Hello and welcome to Astronomy with Mr. Guerin. Today we're going to look at our home, the Earth. We'll discuss its shape and structure and how the atmosphere affects astronomical observations. We'll also learn about how astronomers and geographers divide up the Earth into different latitudes and how these are related to the seasons. We've known that the Earth is round for well over 2,000 years. In 200 BC, Eratosthenes, assuming the Earth was spherical, determined the size of the Earth very accurately. See the video on the size and distance of the Earth, Moon and Sun for more on that. But the Earth isn't perfectly spherical. Its average radius is 6,371 kilometres, but the equator bulges out a bit. This is caused by the Earth's spin, creating a centrifugal force pushing outward, as well as tidal effects from the Moon's gravity. The result is a 21-kilometre difference in radius between the equator and the poles, a difference of 0.3%. The Earth also has valleys, mountains, ocean trenches, and so on. These make very little difference, about 0.1%. This shape is called an oblate spheroid, and you should learn that name. It's like a sphere that has been stretched equally on two of its axes. The shorter axis is the Earth's axis of rotation. The alternative, prolate spheroid, doesn't come up in astronomy. This diagram shows the Earth's structure. It's to scale in the central three regions, yellow, orange and red, but the outer parts have been made larger for visibility reasons. In the centre we have the inner core. This is made mostly of iron and nickel, at high pressure and a temperature almost as high as the surface of the Sun. You don't need to memorise the numbers we're discussing here. Next is the outer core, again made of iron and nickel. The outer core is liquid because it's so hot. The inner core is even hotter, but the pressure there is so high that it's compressed to a solid. Between them, the inner and outer cores spin and create the Earth's magnetic field. Above that is the mantle, which is over 80% of the Earth by volume. This cools as you get further from the core, down to only 500 Kelvin at the top. This is made of mostly silicate rocks. The mantle is solid, but the high pressure is enough that over millions of years it flows like a very dense liquid. On top of the mantle is the crust, the rocks we live on. This is around 500 Kelvin near the mantle and 300 Kelvin at the surface, roughly room temperature. The continents are thick granite-type rock, typically 30 to 50 kilometres thick, and the oceanic crust is thin basalt-type rock, typically 5 to 10 kilometres thick, although in some areas we think it's 0 kilometres thick, exposing the mantle beneath. About 70% of the crust is covered by ocean, up to 10 kilometres deep and made of salt water. In degrees Celsius this time, temperatures range from -2 to +30 degrees Celsius. Remember, you can convert degrees Celsius to Kelvin by adding 273. And above all of that is the atmosphere, made mostly of nitrogen and oxygen gas. The atmosphere actually extends a great distance. Indeed, we recently learned that it goes past the Moon. But it gets thinner as you get higher, and for practical purposes, we say it's 100 kilometres high. The temperature varies from about +15 degrees Celsius at the surface of Earth to -90 degrees Celsius 100 kilometres up. Our atmosphere is crucial for life. It gives the oxygen we breathe, its pressure gives us liquid oceans, and it shields us from harmful ultraviolet, X-rays and cosmic rays. However, it does present problems for astronomy. If we can, we prefer to put visible light telescopes in space, for several reasons. In the daytime, the sky is bright blue when it's not covered with clouds. The oxygen and nitrogen molecules in the air scatter light, and short wavelengths like blue are affected much more. This scattered blue light obscures the stars in the daytime. Near cities and towns, the sky takes on an orange colour at night, as dust in the atmosphere reflects artificial light. This is called sky glow, and makes the sky too bright to see dim stars. This isn't really the atmosphere, but in any developed area there will be glare from shops, stadiums, streetlights, cars and so on. This ruins our eyes' night vision or dark adaptation. Twinkle, twinkle, little star, how I wonder what you are. Well, hopefully you know by now what a star is, but why do they twinkle? As a star's light moves through our atmosphere, the air refracts it, changing the light's direction. but refraction depends on the air density, which depends on temperature. Light reaches us by paths which shift slightly as the different air masses move around. We see this as twinkling. Different weather patterns make this effect more or less strong, and we call this seeing conditions, which vary from night to night. We don't see this with planets because they're brighter in the night sky, and the twinkling effect averages out. But stars are so far away that hardly any light reaches us, and they appear as only a single point in the sky, so twinkling is much more pronounced. Now we're going to talk about the Earth's tilt and the seasons. But first we're going to divide up the Earth using lines that are useful for astronomers, geographers, navigators, and many more people. This map shows the whole Earth, stretched out so that we can see it all at once. Our first division is an obvious one, the equator at 0 degrees latitude. For a complete explanation of latitude and longitude, see my video on celestial coordinates. We have the north and south poles, points at 90 degrees north and 90 degrees south. Any line drawn across the surface directly between the poles is called a meridian, and the prime meridian is the meridian at longitude 0. Again, see the celestial coordinates video for more on this. At 23.5 degrees north and south are the tropics. 23.5 degrees north is the Tropic of Cancer, and 23.5 degrees south is the Tropic of Capricorn. If you forget which way round they go, it's easy, they go in alphabetical order. At 66.5 degrees north is the Arctic Circle, and at 66.5 degrees south is the Antarctic Circle. Arctus is Greek for bear, because Ursa Major, the Great Bear, is high in the sky here. Let's look at a more normal round Earth. The rest of this video will make much more sense with this round Earth. But the Earth is actually tilted. Its polar axis, about which it rotates, is tilted compared with the ecliptic, our orbit around the Sun. The black dotted lines show the Earth's axis and equator if it wasn't tilted. The Earth's tilt is 23.5 degrees, compared with the sunlight reaching us. Note that the horizontal black line, which is parallel with the sun's rays, just touches the green lines, the tropics. The tropics are at latitudes equal to the Earth's axial tilt, 23.5 degrees north and south. On the Tropic of Cancer, at midday, the sun is directly overhead. As the Earth revolves around the sun, different latitudes on Earth will see the sun directly overhead at midday, but only locations between the Tropic of Cancer and the Tropic of Capricorn. At the equator, daytime and nighttime are both 12 hours long throughout the year. Now I've highlighted the temperate zones between the tropics and the Arctic and Antarctic circles. Look at the northern temperate zone. As the Earth rotates, any location here will spend more time in the sunlit half to the right than in the unlit half to the left. This is summer in the northern hemisphere. The daytime is longer than the nighttime. In contrast, locations in the southern temperate zone will spend more time in the dark half than the sunlit half. This is winter in the southern hemisphere. Night is longer than day. Also, look at the sun's rays hitting the northern temperate zone. Here we have about 6 rays. Compare that with the southern temperate zone, which only gets 3 rays. This is why summer days are hotter than winter days. A given area on the Earth's surface gets more heat and light in the summer than in the winter. The Arctic regions are past latitudes 66.5 degrees north and south. 66.5 degrees is 90 degrees minus our axial tilt of 23.5 degrees. In other words, they're 23.5 degrees from the poles, and the vertical black line meets the blue Arctic and Antarctic circle lines. Here, the Arctic circle is in constant sunlight. As the Earth rotates, the sun doesn't set. The Antarctic circle is in constant night. The sun doesn't rise. As the Earth revolves around the sun, the region that is in constant light or darkness gets larger and smaller. On the Arctic and Antarctic circles, you get 1 day a year when the sun doesn't rise, and 1 day when it doesn't set. But at the North and South Poles, you get a 6-month day and a 6-month night. Now that we understand the effects of Earth's axial tilt, let's look at how that produces the seasons. The Earth's tilt stays the same as it orbits the Sun. The tilt does vary over thousands of years, but we can ignore that over a human lifespan. This image shows the vernal equinox, which is where astronomers start measuring orbits from. This is around the 21st of March, when the Sun appears at the first point of Aries. Again, see the celestial coordinates video for more. The northern and southern hemispheres receive equal amounts of light, and everywhere on Earth has 12 hours of day and 12 hours of night. Equinox means equal night. The exceptions are the North Pole, where the Sun is rising, and the South Pole, where the Sun is setting. Everywhere on the equator will see the Sun at zenith at noon. In the Northern Hemisphere, this marks the first day of spring. I'm going to talk about northern seasons here. For the Southern Hemisphere, everything is the same 6 months later. In 3 months, on the 21st of June, it's the June solstice, or summer solstice in the north. We receive more light and have the longest day and shortest night of the year. The Sun doesn't set anywhere north of the Arctic Circle, and is at zenith at noon on the Tropic of Cancer. This marks the first day of summer. On the 23rd of September, it's the autumnal equinox. The 23rd isn't a typo. It would be nice if all of these were on the 21st of the month, but our human calendars, combined with leap years and our elliptical orbit, make things a bit messy sometimes. Just like the vernal equinox, day and night are 12 hours everywhere, and both hemispheres receive an equal amount of light. The Sun sets at the North Pole and rises at the South Pole, and is at zenith at noon on the equator. In the sky, the Sun is in the first point of Libra. This, of course, is the first day of autumn. And on the 21st of December is the December solstice, or winter solstice in the Northern Hemisphere. We receive less light and have the shortest day and longest night. The Sun doesn't rise anywhere north of the Arctic Circle, and is at zenith at noon on the Tropic of Capricorn. This is the start of winter. A common misconception is that summer is when the Earth is closest to the Sun. Of course, if that were true, the northern and southern hemispheres would both have summer at the same time. In fact, we are closest to the Sun on the 4th of January in the northern winter. The difference is only about 3% though, and our axial tilt has a much greater effect on the seasons. This video has shown you everything you need to know about the Earth's structure and seasons. There are more related things to learn, in particular how we keep time on Earth, which I'll cover in a future video. Thank you for watching. Goodbye, and have an excellent day.